you can't go ahead and pin particles in a liquid and say RFOT is correct. You see, everything that I've shown you is only of the context of pinning. I've never shown you whether the pinned liquid and the bulk liquid behave the same way. Okay? So they basically said everything that people have been doing with pinning was wrong. All right? And the idea was, of course, whether, yeah. I think sodium chloride. Yeah. If I change? Yeah. No, so you see, like I said, I am at this stage only talking about individual particles interacting via some sort of a screen Coulomb interaction. All you will change by changing the size of the counter ion or the valence is to change the Debye length. So you just put in an effective radius that is larger. But other than that, all of this should hold. Everything that I've said should hold.
Is spinning a portion of a liquid?
Yes.
Is not qualitatively different from sort of aging quality?
These are quench disorder, so they never break the cage. So the relaxation time is infinite.
Yeah, but if one can somehow like vary over that particular variable and like reach a state where you can play around with how much you have caged it, or how much you've pinned.
All of this is done for infinite pinning in the simulations. You could do it with finite strength and ask what it affects. I think there's some study. I'm not really aware of what they found. But the goal is, whether all the findings that I showed you so far will it even go to a system in which you don't have to pin it, okay? And that's okay. I really have like a couple of minutes, so.
Can you pin one single particle in its entirety?
Yes. Yes.
So, and
yes.
How does this affect dynamics? So now if you do exactly one, maybe there are too many.
Yes.
But if you randomly pin some part.
Yes. See, yes. So the question, the trouble is, in one of the studies which questioned the pinning approach, the minute you freeze a particle, you have a layering effect coming out. So people know that if you take a liquid near a wall, you have this layering in the density because the liquid molecules are facing a rigid, right? Now when you pin a particle, what you see is in your pair correlations, you see some sort of a ripple of this pinned particle.
Isotropic ripple.
Isotropic ripple. But the trouble is that is not the same as the unpinned liquid because there are no ripples in an unpinned liquid. So the question is, how do you know all the findings in the pinned system, growing size, everything, applies to a real liquid? Okay? So which is what we did. And the idea was that we exploited a simple fact that in real liquids, in which you don't have to turn on the pins by artificially, the slowing down is because there are certain configurations of particles which lead to a packed geometry, and you can identify these configurations. That was the idea behind the approach. So what we're going to do is we start with the liquid, we grid the system into boxes, and what we do is we basically find the configurational overlap over the relaxation time called tau alpha, and we find the slowest particle in the system. In this system, we find the slowest particle, the particle that moved the least, that never left the box. Okay, it has a very high configurational overlap. And what we're going to do is we're going to call this the self-induced pin. Okay, and now there is no external pinning. Around the self-induced pinning, you can now ask the question whether you see the non-monotonicity again. Okay, I will not walk you through all of this. We did the whole exercise.
So this self-induced pin remains for how long?
Over at least tau alpha. You see, so the difference between over at least the relaxation time.
Oh.
Now, you see the difference between our approach and what was proposed in simulations is that when you pin a particle using the simulation or the tweezers, it is pinned for many, many relaxation times.
Yeah.
It's quench disorder. Ours is pinned over tau alpha. But you can ask all these questions over tau alpha. You can ask if you see the non-monotonicity, right, over that length scale. And we find that you once again find a growing static length scale that grows faster than your G of R, which is your pair correlation function, and you also see the non-monotonicity. How is what different from dynamical?
Whatever you calculate.
Oh, so this quantity is related to dynamical heterogeneities. This quantity is what is remnant after relaxation has happened. So this is really like a static order. So you have looked at it over tau alpha, So you look at particles that stayed in the same box or the same region of space, or the same, adopting the same configuration over many, many relaxation times. So this is really the dynamic length scale, and that's the static length. Okay, and so what basically we found is that you pin or don't pin, the non-monotonicity and this thing basically survives. Okay, so we were a little bold at this stage, and what we did is, so if this is basically your sample, this is your pin, okay, now you can define an interface as a region that delineates something that relaxes from something that doesn't relax. That's something coming back to what you pointed out. Okay, but look, I'm not looking at particle identities right now. I'm looking at configurational space. So I'm looking at an order parameter in which whether configurations remain the same or configurations don't stay the same. And that's really what RFOT says is a mosaic. Okay, now you can go ahead. So this is my, okay, I'm running out of time. So I'll come to, so this movie is beautiful. So I'll show you this movie. Okay, so what you're seeing here is the configurational overlap around a self-induced pin. Okay, and the maroon regions are regions with a high configurational overlap, and the yellow regions are ones with a low configurational overlap. And I can define an interface around it. Okay, once I define the interface, what I can do is I can look at the fluctuations of this interface because I have access to time data, and from the fluctuations I can tell you what the surface tension is. Okay, so what we did is we went ahead and used what's called the capillary fluctuation method. The idea being that if you have a fluctuating interface, you can decompose the interface into all its normal modes. Okay, and the spectrum of amplitudes of the normal mode is supposed to go as an interfacial tension times 1 over k squared. So that is the plot of the LAK squared, so it's essentially flat. But more importantly, we were able to pull out, the surface tension as a function of phi. So these are the surface tensions of regions of high and low configuration overlap. This is for self-induced spinning. This is for the frozen wall. Okay, and this is what RFOT says should happen. Okay, so. Well, I'm a pro RFOT guy, so I think it's correct. But if you show it to DF, you'll just say this is all complete garbage. So it just depends on which side of the lines you're on. So we have to pick the referees carefully. But that's the way it is. All right. All right. So we basically see a growing surface tension, and that holds whether or not RFOT is correct or DF is correct, because this is experimental observations. Okay. And one last bit, which is, so we looked at all the mobile particles once we had these mosaics, and you will imagine that if I have two mosaics, the particles of the interface can only move along the length of the mosaic. So you can look at anisotropy of particle motion, and you see all of, so this is the mosaic, and these particles are all elongated along the length of the interface. Okay, that is something that we found in green boundaries a long time ago. So with that, I just finish. So we found the non-monodic
velocity mobility tensor, or your mobility tensor is basically order parameter.
I don't have a mobility tensor, no? I have
because you were saying that particles are on the interface is only moving in one direction.
Yeah, that's because I have two configurations of particles that are frozen.
That means that it's only in a particular direction.
Yes.
It's not isotropic.
It's not isotropic because the cages are weaker along the length of the interface.
So inside you it's isotropic.
Yes.
So that's the order parameter.
Oh, so we didn't use that. We just said particles that retain configurations. But I'll just maybe we can talk later. Yeah. All right. So to conclude, we saw the non-monotonicity. It's not a feature of the pinned liquid. It's also something that you can see in unpinned liquids. And we have this surface tension, which we think we have measured. We don't know if this is what the mosaics are that RFOT says, but it's a plausible candidate. Okay. And this is something that I don't think we have resolved, but I'll be happy to take questions if any. Thanks.
Questions?
Yeah.
So you mentioned in the beginning that the configuration entropy of the glass, it goes below that of the crystal. It is, so physically what does it mean? How do I visualize it? How do I understand?
You don't visualize it. You can't, because, yeah. So the trouble is the ideal glassy state The only thing that we know is that it is fallen in such a deep minima that for all practical purposes it's an equilibrium disordered state. That's all. Anything more is anybody's guess. Yeah. Yeah.
I mean, is there a spinning threshold, or I mean, how do you decide the strength?
Of the what?
You have some pinning threshold, pinning sites that you.
Oh yes, so you mean external or self-induced? So I did both. External pinning. When you say pinning threshold, how well do I hold the particle?
Yeah, I mean, I'm guessing not all kinds of pinning are going to give you the same thing.
Yes, correct. So in the limit of weak pinning, I have the unconstrained liquid. In the limit of strong pinning, in experiments when you hold it with the tweezer, you really don't freeze all the motion. They're still rattling about. So all we care about is, after we pin them, did they break a cage? Is the pinning strong enough to suppress cage breaking? So when we show the wall movie, you would have seen the wall particles also rattle a little bit. Yeah, but they don't break cages ever. Yeah. Yeah. Please say it again. Please, can you just repeat your question again?
Below graph is going upward direction and its non-monitors is fall down, so the data symbols.
This one. Yeah, it falls down.
So if 0.8, this data up to 0.8, suppose it's going 0.9, so what is it like? Well, I think the point is
how the graph
why it's showing them.
They will ask you, if you have all points, to see that it's a real.
So you see, the trouble is, this is phi MCT. When you say phi MCT, it means the time that the volume fraction at which relaxation times were so huge that you really can't equilibrate the system. Okay, so getting this point alone is like months of labor. One more, and they seem to have bought it, right? With that one point. I wasn't sure they would buy it, but they're so hell-bent on saying that RFOT is correct that that one speck of data that you show is enough to convince people. But then we did show that there was a changing shape of clusters, and that is something that's more continuous and more systematic. And the surface tension measurements, that I showed you this. The sharp change. So you can. This is in the mean field. If you work in finite dimensions, it turns out that it follows a profile like this. Okay. Yeah. Yes.
In such system, do you see glass-to-glass transitions? Two kinds of glass
Yes.
with different relaxation times or something?
Okay, so I don't have any stuff here but what we did is, a little while ago, we were looking at ellipsoids interacting via short-range depletion interaction. So these are really sticky interactions. Two particles see each other only when they stick. But then once they're stuck, they stay bonded for some time. In those systems, there's a prediction for a glass-to-glass transition. It is a transition from an attractive glass to a repulsive glass. And there are certain features that are predicted around the transition, like a logarithmic evolution of relaxation times. We saw all of that, but not in this scenario, not in the system that we have.
I have more basic questions about your experiments.
Yeah.
So, to do the supercooling.
Yes.
So in your system, there is some temperature is being changed.
Area fraction. Area fraction. I don't have a temperature in a colloidal. All I do is.
There's some effective. So, but is there some equivalent of a thermalization time?
The thermalization.
That has to be much faster than.
Oh, so that happens on the time scale over which the kicks that I get from the solvent gets randomized, and that happens on a very short time scale. So my particles effectively see a nice thermal bath. So the velocity autocorrelation time decays in about 10 to the minus 6 seconds for about a micron size bead. All my data are in thousands of seconds.
So this time scales are widely separated.
Which is why I get to talk about it as a purely thermal system, which is why I am allowed to do all of which I did. Yeah.
Your experiment said confined.
I have two cells, yes. Yes.
So you have
Wall effects.
strong and dynamic effects. So that gives you another dense scale in the problem.
So what we did do is that one way to isolate the hydrodynamic effects, we didn't do it, but there are papers on it, is that if you're coupled to a wall, you have the vortex shedding when you move a particle in a suspension, and it turns out that length scale is very small. So these particles are effectively acting.
But your Stokelets are 1 by r
No,
potentials.
no, no, yes, it's 1 over r, but for when you take aggregates of particles, it is much faster. When you take the kind of densities that we are looking at, it decays much faster. So there's some study, I can look at that. And
But that doesn't mess up with the competitiveness in your system.
no.
Okay, there are no more questions. Let's thank you.